Okay, and a good morning to everyone. And that was Joni Mitchell still, is that correct? The album is Shine, and do I have the, yes, I have the mic on. And what was the title of that one, Ernie? This Place. This is the place for mathematics. It's a good tie-in. Now, yesterday we started 7-1. Didn't have an opportunity to get very far in 7-1 because of the questions we did on the preceding material. But we're also going to spend some time in 7-2. Now, we are focused, at least in part, on 7-1 with probability. And I talked about a dice game, and just a comment for you. If we look at a deck of cards, because that's covered also here, we're talking about the standard 52 cards. We're talking about 4 suits, where you have the hearts, the diamonds, the spades, the clubs. And then you have, in that, 4 aces. You have the face cards. And so there are questions. So if I just have a standard deck of cards and I ask you, what's the probability of getting an ace? There are 52 possibilities. 4 of them are successes. So you could list 52 different, if you will, cards that you can get from a deck. And of those 52, 4 are aces, the ace of hearts, the ace of clubs, the ace of spades, and the ace of diamonds. So it's 4 out of 52 in the story. Now, you can reduce that to 1 over 13. But I want you to realize in probability, for the most part, at least as I present it in the statistics course that we have here, I tend to leave those probabilities as fractions rather than decimals. So that's very common. Now, there's another ratio that we talk about, and we talked about earlier when we were looking at the Fibonacci numbers. Okay, remember the Fibonacci sequence. And in the Fibonacci sequence, it was 1, 1, 2, 3, 5, 8, 13, 34, 21, 34, 55, 89. And we talked about the 55 and the 89 in particular because that's on your speedometer if you have an old-fashioned one, where it has a little needle that goes around and you can watch it instead of the LED printout, or I should say not printout, but where you just see the numbers. And the 55 and the 89 had a ratio of roughly 1.6. And I commented that that is what we call the golden mean. So as I go to the board, the golden ratio, or the golden mean, and the reference to this is, again, in Greek architecture in your book it's referenced. But this is roughly 1.6180,339 and more to come. And that's just the ratio of the Fibonacci numbers at the moment. I mentioned that this is also done in art. And it related, if you remember, to what we called the golden rectangle. Okay, so you had a golden rectangle. And the idea of a golden rectangle, just to tie some things together, and I'm surprised in some ways to see this in the book, but I'm pleased. But if I have a rectangle, and if it is a rectangle where I cut off a square, does that look like I have about a square there? Reasonably so. If I cut off that square and the resulting rectangle has the same ratio of length to width as the original. And boy, that is clearly not. Let's see if that looks like a rectangle there, a little bit better. So let me do that there. And on this side, it looks like that needs to come down a little bit more like this. So let me clean that up a little bit. So at least on the screen, it looks better. Now, if I cut off a square, and I'm estimating this somewhere in here at about a square, that if I do that, I get a new rectangle. And so the argument was if this new rectangle that I get cutting off a square has the same ratio of length to width as the original, then I will have a golden rectangle. And so the way this is often done is to call this side here X. Okay? And then what I want is to consider this as x here, and if I consider this whole value here, okay, as being 1, then this little portion here is 1 minus x. And this is still x here. So if I look at what I'm doing here in terms of ratios, and a ratio is simply a fraction, then the argument is the length to the width was 1 over x. And that is in the same ratio as the new length for this small rectangle as x to 1 minus x. And that becomes what we consider a proportion. A proportion is simply two fractions that are equal to each other. And I commented on this to you about proportions from Greek mathematics, and we had two fractions in this form, a over b equal to c over d. We made the comment earlier that we can cross multiply and argue that a times d equals b times c. So this was your cross product, hence its name. Now from early Greek mathematics, we didn't write the proportion in this way. We said a is to b, meaning a ratio. So a is to b, and we oftentimes use a colon there, is to b as c is to d. Now you can write that out in an English phrase. I'm using the colon to say a is to b, meaning a over b. These were called the middles. These were called the extremes. And for the middle, we use the word mean, like an average. So the product of the middles, or the means, was equal to the product of the extremes. Well, that's exactly what I'm getting here. And in this 7.1 and 7.2, I'm sort of blending some things together here because we're doing both this morning. If I look at this original proportion and I look at the LCD, it's equal to b times d. If I multiply both sides by the LCD, I get this statement. So one more time. If a over b is equal to c over d, and I multiply both sides by b times d, and I think I need to make that look larger because it's not reading well on the screen. The LCD is going to be a product. Well, I can't say necessarily that it's the LCD. I should stand corrected there. It's certainly a common denominator. Now, if b and d are relatively prime, it is the LCD. But I'm going to treat it as the common denominator, and if I multiply BD times A over B, and I multiply BD times C over D, as long as B and D are not 0, I can cancel, because that's really over 1. This is over 1. So on the left side, I have AD or DA. We usually write it alphabetically. And on this side, the D's cancel, and I'm left with BC, and that's precisely what we were saying by the cross product. Now, if I use that idea, and I go back to this golden rectangle, take the cross product here. What do you get in this problem here? The proportion is going to give you that 1 times 1 minus x is equal to x times x. Agreed? And so, if I multiply things out, I'm going to have 1 minus x is equal to x squared, and I could go ahead and rewrite that. Okay? And I can rewrite it as x squared plus x minus 1 equals 0, getting everything on one side. Question? Now, wait a minute. I understand what you're saying. Let's come back. Let me clean this up a little bit. Again, I'm not getting things as neat as I usually like. I'm going to rewrite this a little more larger than it was, because the question's been asked about that. You cannot cancel these x's. You can't cancel these x's. There's an equal sign between them, not a product. If these were multiplied together, then you could cancel them. But they're not, so the only thing you can do is cross multiply. And we get an equation. And this is the equation, x squared plus x minus 1 equals 0. Now all I did, I added x to both sides, and I subtracted 1 from both sides, so I would have the 0 here and all this on the other side. It's more common to write the variable expression on the left side. The value of x that makes this true is going to be that 1.618039. Now, there is something that we're going to get to as a way of finding an answer to an equation like that. Okay, as it turns out, the way I've written this problem, there are two different answers that are possible because it's second degree, and I told you that there would be two solutions when we have a second degree expression in one variable. One of them is going to be 1.6180 plus, and the other one's going to be a 0.618, and as it turns out, one will be positive and one will be negative for this particular problem. So there will be two different solutions that I'll get out of this, one positive, one negative. And you find reference to this golden mean. And let's slide over a little bit more, Ernie, so I have some spacing. Thank you. If we go to that value, this is what's called the golden mean, and this is oftentimes involved in such problems. So if you look at some of the illustrations that are given here, and I'm going to come back to the document cam in a moment, but I'll come back center first, Ernie, if you don't mind. Just come back center. And the problems related to this, and I've got to see where I am now in terms of the problems. And I'm on the top of page 504. This is called the golden ratio or the golden mean, and I've referenced this in the past. The ratios of 0.618, I just mentioned to you, are also involved with 1.618. And this, I talked to you about this first ratio, I believe, in Math 10, but I did it in a slightly different way. This happens to be the ratio taking where your belly button is to the top of your head versus the belly button to the bottom of your feet. I took the belly button to the bottom of your feet to your total height. And the argument was that that came out 1.618. Same argument. Here's the center of the eyes and the top of the head to the bottom of the chin. In art, we're getting a 0.618 instead of going for the 1.618. Shoulder to top of head, navel to shoulders. I think most of you are familiar with Da Vinci's painting of the nude that's used as a book plate oftentimes to say this book belongs to somebody, and it is demonstrating really the golden ratio in the human form. Now, just be aware that in art and in music, it's there in much of what we do. And that's what this illustration is trying to present to you. What is not done is coming back to the board where we look at this equation. And one of the things I do in an algebra course at about this point in the semester, a little bit later in an algebra course, is do what we call a quadratic formula. Now, this is referred to as a second degree equation. It is also known as a quadratic equation because a quad is like a square. So instead of saying a squared equation, which sounds awkward, we call it a quadratic equation. But there's a formula that can be used, and this is mostly just informational. It's something I wouldn't expect you to use, but I want you to understand that the general form of this equation is written this way. So A is 1, B is 1, and C is negative 1. This is just the general form. Now, this is referred to as quadratic, and one of the things I've wanted to come back to for some time that I didn't say before that should have been said, this is called a linear equation. So this is going to be linear, and this is going to be quadratic. And it has to do with the exponent. First degree, one variable, linear. Second degree, one variable, quadratic. Now, as it stands right now, these are in terms of single variables. Very early on, we look at two variables. Instead of saying this is equal to 0, we just say y equals each of these. So these are going to relate ultimately to these forms. Now again, just informational. I'm not asking you to do anything with these. But the point is, you know how to plot ordered pairs. We did that in the simple closed curve unit. We plot ordered pairs. Well, if you look at the ordered pairs, x, y, that we could use for these two different equations, all the ordered pairs that make this one a true statement are on a line. So this is actually the equation of a line, and hence the name linear. So this gives you a line on a graph. This one up here, second degree, gives you a conic section. It gives you a parabola in this case. So this is actually going to be the equation of a parabola. And we talked about parabolas. So these become very much part of what we do in an algebra class. And these are referred to simply as equations in one variable, and we find a solution. Now, as I mentioned, there's occasionally some very nice formulas that are involved, and I want you to see this one just to be aware of what it looks like. We take our a, b, and c, and we would say x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Now that is referred to as the quadratic formula. So you just look at it and say, okay, I've got a formula. And what I'm hoping at this point is you look at something like that and say, okay, it's another formula. I'm trying to get you past the point where you see a formula like that and go, oh God, another formula. What will I do? That you see something like this and don't panic. Because I could say, given this formula, and given that up here, a is 1 because there's a 1 in front of the x squared, there is a 1 understood in front of the x, I could say that a is 1, b is 1, c is minus 1, and you get a very interesting result. Because if I take these and just substitute into here, I'm going to bring this up to here now, I would have x is equal to, so the b is 1, correct? So minus 1 plus or minus the square root. Now b squared is going to be what? 1 if b is 1. So I have 1. Then I have minus 4, and a is 1, and c is minus 1, correct? And that's over 2 times 1. All I've done is substitute. Now that's an expression that's awkward. What we're supposed to do, order of operations, we go to the radical first. So that is minus 1 plus or minus the square root of 5 over 2. Minus 4 times minus 1 gave you a plus 4. 4 and 1 is 5. Do we agree? I just want you to be able to agree to the substitution, not asking you to understand where this equation came from. We do that in the next semester. Now I'm going to tell you some information. The square root of 2 is roughly 2.236. I mean, the square root of 2, square root of 5. The square root of 5 is roughly 2.236. So this is minus 1 plus or minus 2.236, and I'm going to divide that by 2. And this would have been a good problem for this lesson because it's with decimals. So that means I take minus 1 and minus 2 something, and I also have minus 1 plus 2 something. So what I'm going to do is take the two negatives. So that's negative 3.236 divided by 2. And what do I get? Well, that's negative 1 6, okay, 1, 8, and if I kept going, you would have had the 1.6180339. That's exactly where that number came from. Now this happens to be a negative one, and the other is going to be 0.6180339. So as I come back to my statement here, this one would be negative, and this would be the positive solution. And that is one way we solve or find the solution to a second-degree equation. And by the way, this will work for any second-degree equation. There are faster ways of doing some problems through factoring that we talked about in the distributive property in reverse. But what's neat, here's a case where we see, as we slide over a little bit more here, substituting, getting decimals, and doing a problem very consistent with what we did in Chapter 6, getting decimals. Now there's a question. Kim?
Why do you go positive 1 and negative 1? Shouldn't they both be negative?
Here?
Above.
Here?
Where you were at the first
Here?
one. Yeah.
Well, do your multiplications first, correct? This is a product, negative 4 times 1 times negative 1. This was, okay, you got it straightened out. This was b squared minus 4ac. A was 1, c was minus 1, and so I take that product and I get plus 4. Anybody else there? Now, in fairness, you need to understand that doing what I just did here, that would be a whole chapter in an algebra course. One whole chapter. And showing that this works would be a major problem on both the final and a midterm. Okay? And so I would expect you to be able to go from here to here and show me that's what you get. And that, again, would be at least 2 days of lecture and discussion. So I'm giving you a kind of overview with intent. Because part of what I think my role here in a pre-algebra is to give you kind of, okay, this is what's going to happen. This is where you're going. And it ties very nicely with where we've been, to the golden rectangle. And as I come back center now, there's a comment here on the bottom of that of interest on page 504, referring to the Parthenon. Okay, so as we look at that, this is the Parthenon. This is the building in ancient Greece, which had golden rectangles in it. Okay, and of course, references are made to music and instruments created with the golden mean or the golden ratio. So that was another topic in that first intro, along with the idea of a ratio. I mentioned yesterday briefly something that also has, and this shows some very good insight from the author of this text, to the slope of a roof or of a ski slope, of anything that has an angle to it, and we talk about vertical rise and sometimes called the run. So what I'm going to do is go to the diagram down here and look at what we are seeing. This is a right triangle, clearly. Okay, I hope you understand that. And this is a case where we have 8 inches here and 12 inches running here. So this is a little bit like what happens on a stair step. So this is where you step, this is the rise, and then you go another and stair step up. But if you look at the ratio here of 8 inches to this 12 inches, that is called the slope of that line, the slope of that roof, the slope of that incline. You can think of it in a variety of ways. So the 8 over the 12 is going to be called the slope. Yesterday I mentioned to you that we have a name for that. It's going to be called the tangent, T-A-N, abbreviated, but tangent. And I've made reference at times. I'm trying to think what I can do up here and draw, and I can't. So Ernie, I'm going to have you go to the sideboard. I'm going to put something in context here. in a more general way to tie some ideas. Again, just a lot of what we're doing is vocabulary and understanding how things get tied together. So I'm going to come back to this diagram, and I'm going to refer to the left side of this. This is the connection. The ratio of the vertical rise to the horizontal length, and the horizontal length is often referred to as the run. So we have rise over run. But I'm going to draw another diagram for you briefly. I don't know how well I'm going to do, but we'll give it a shot. I have a circle. Now, you are aware there's a center of the circle, and from the center of that circle, I can draw a line segment, and we call that line what? The radius, correct? Now, if I draw another line touching the circle at one point, and my line's a little bit too thick because it should be just touching here at this one point, so that this line touching is at right angles, and I don't have it quite at right angles, I note. That is called the tangent line to the circle. So this line I drew, touching the circle in only one place, is referred to a tangent line. And it happens to be perpendicular to the radius. So if I have a problem where I just create a right triangle, and I draw this coming across here as the diagonal, and this is your right angle, and this I'm going to title now A, just a minute, I'll do, yes, A, B, and C coming counterclockwise. Then this is called angle A. Okay. And this is called angle B. So the slope of line AB, otherwise I'm going to A to B, okay, is going to be, and what we do is take the side opposite the angle A is little a, the side opposite angle B is little b, and that's not arbitrary. That's common notation across the world. So the angles, big letters, the sides, little letters, and the side opposite the angle takes the little letter of that angle. So angle B, little b. Angle A, little a for the side. Then the slope of the line is going to be A over B. And we call that, later on, if you were to keep going, the tangent of angle A. So we give a name for that. It's the tangent of the angle, and it is the slope of the line. So again, just information, and the TAN is referring to tangent. And I said that comes from a field of mathematics that is oftentimes used or presented in a second semester of algebra, second year of algebra, called trigonometry. And it's used in surveying, by the way. And we do surveying, we estimate heights of buildings. So for example, if this is the tree that you're looking at, and here's the base of the tree, and you know how many feet you're out here, and you know this angle, you can get the height of the tree. That's one of those things in the old Boy Scout manuals, that if you were out in the wilderness and you want to know the height of the tree, you could do so. Not that it would be particularly relevant, but it gave you something to do when you're lost. Okay, let's come back to the book. So we're opening up a lot of doors here, and I think, again, the point in this, and I'm going to, again, focus on this statement because I want to, this is anticipating a bundle of problems in the future. Okay, let's come back to that. I'm going to come back to my diagram and open the door a little bit further to where you're going to be. Coordinate system, right? This section is covering so much to come, and if you don't know what you're getting out of this section, it's sort of like, well, we didn't tell you the whole story, using old Paul Harvey statement, who recently died. I have my 2 points. Okay? just like I had over here, A and B. So this was point B, this was point A. Okay, and I want the slope of the line. If I had these 2 points, I would do something like this, coming across here, coming across here, and coming down here. Now, what we end up doing, and I'm going to get rid of the A and the B for the moment and just call this point 1 and point 2. 2 points. You know they are ordered pairs. So I'm going to call this point x1, y1. And this x2, y2. Now technically, I should be saying sub 1, sub 2. I made a reference the other day to a superscript. That's what an exponent is. This is a subscript. So we have subscripts, we have superscripts. So what is this value here? That's the rise, correct? Well, it's just the y1 minus the y2. So this was at y1, this is at y2. So the slope, coming back now, if you will, to the book in the document cam, rise over run. Where this is going is that the rise is just y1 minus y2. And the run, this is x2, this is x1. Okay. Did I get that right? That's going to be yes, and so I have x1. So this is y1 minus y2. That's the distance there. And this is x2 minus what? x1. Now I've got to be careful here because something I have screwed up in terms of this will be a negative in this case, which is the way it should be because this line is going downhill. The formula usually, if I were to have these points in this rough sketch where it's going uphill, then the same thing I've done will be y2 minus y1 over x2 minus x1, and this is called m, which is the slope. So this is the more general formula, and I unfortunately had all the way back to the first triangle I drew, I had a line that was going downhill as you go from left to right, which means its slope is negative. If it's going uphill, like I've drawn here, then that would be a positive slope. And this is the more general formula. That, you spend a whole section, 2 days, at least, if not longer, in an algebra class just on slope. So the idea of slope, tremendously important in the algebra class. And that's why in pre-algebra to see it here is really nice. But I think I have to put it in context for you. In part, and I've been reflecting in this a whole lot on my bike rides and the discussions Sarah and I have been having. What kind of background are we trying to give you out of a pre-algebra? And part of my concern is that when you walk into an algebra class and you see something like this, say, yeah, I remember we worked on that, and then go back and reference it and try to pull things together so it doesn't go so fast on you. Here I get to present it to you, and I don't have to hold you accountable, but I do give you a reading of it so you can hear it, see it, and I hope be better prepared. So let's go back to the document cam. Now, the only other thing of particular interest here, and this is more from a consumer's point of view, and I used to have in the Math 10 a complete unit on comparative shopping, and then I pulled it out because I had to give up some things. And we still don't cover everything in the Orange Book. But I had a unit on comparative shopping. And on comparative shopping, you did unit price. So the idea, the unit price idea, is involved with page 508. And this you find done in stores as a service to you. The idea is you have a box of cereal or something, And here are 2 boxes of cereals. Okay, and one of them is $2.45 for 15 ounces. The other is $3.59 for 20 ounces. And of course, the popular wisdom is the bigger box is the better buy, correct? I mean, that's usually the sense of what we have, the big economy size. Well, here's a case where if you simply have, instead of 15 ounces down here, have 1 ounce, so you divide top and bottom by 15, you find it's roughly 16 cents an ounce. Same calculation here gives you roughly 18 cents an ounce. So which is the better buy? The smaller box. And as I say, this sort of goes under truth in shopping. And this is done for you on the shelf at most good markets. They give you the unit price. Now, we have a whole culture up until this year predicated on a Costco, Winco, large box store where you can buy large quantities. So instead of getting a small box of 20 ounces, you can get a gargantuan box that has 90 ounces in it and takes up half the shelf space in your cabinet. You hope that that's less expensive. Not necessarily so. So as I indicate to you, this is just in terms of what's the better buy. Enough said, I hope, in that process. So I think with what we've done there, 7-1 and the problems I've selected shouldn't give you much of a hassle. There's one other, I guess, comment I should make. We talk about how many miles per hour you go. That's a fraction where we have the miles in terms of 1 hour. And so if you look at something like problem 39 on page 513, which is a problem I selected, it tells you that Tara drives 306.9 miles in 4.5 hours, and you're supposed to find out what? What are her miles per hour? Well, that's a rate, as we call it. I'm going to come back to the side for a problem we've talked about as a word problem, and just remind you of this formula. Distance equals rate multiplied by time. So if we look at R, it's d over t. So your miles per hour is a rate. And we usually refer to this in miles per hour. So if I go back to the problem that's just given, and I have 306.9, and it's in 4.5 hours, this was miles, this was hours. We refer to this as an average speed then, in which you divide 4.5 in here just to get 1 hour. And that then gives you the miles per 1 hour. So if you want to get 1 hour, divide here by 4.5 and divide here by 4.5. Or you can think of multiplying top and bottom by the reciprocal, given your choice. And that gives you miles per hour, the usual thing. Miles per 1 hour. We did this in the how much unit. Okay? And we talked about how when you get miles per hour or so many cents per ounce, the 1 ounce is understood in the denominator. The 1 hour is understood in the denominator. So I don't think that's new. Let's come back to that problem for a minute. Enough said there. I want to go to 7.2 because there's some really important transitions that we're talking about here. And if you aren't careful, they appear to be lost in just glossing over everything. Now the proportion, I told you earlier I was covering 2 sections at the same time. Here is the cross product of the proportion A over B equals C over D. And so we talk about solving a proportion. Okay, so I have A over B equals C over D. We know to take the cross product. And I'm going to come off there for a moment, and I'm going to do a really non-subtle segue here for a moment. And I'm going to put this problem in context. And this is going back to simple closed curves. So leaving that on the screen for a moment. If you had 5 points out of 12 inside a simple closed curve, so you just got lazy, you're going to plot 12 points. So you had 5 points on the top, 12 points total. And the area of the grid is 8 square inches. Bingo. A proportion. And that's the way I ask you to solve this problem with proportions. And the argument is you can do what? Take a cross product. So you say 8 times 5 is equal to what? 12x, and now you know how to get rid of factors. You're going to divide by the factor. So I divide both sides by 12. I get x over here, and of course this reduces. You can take 4 into here goes 2, 4 into here goes 3. So this is 10 over 3, or you would say 3 1/3 square inches, if it were square inches. You've done this before, okay, as a way of solving problems. Now I want to kick this a little bit further along for you because I'm going to come back to the how much unit now. Okay. You went ahead and you paid $5 for 12 pounds. How much should you pay for 8 pounds? I'll write this out. For 8 pounds. Now, we did that as a how much problem, correct? You said I can take my $5 over the 12 pounds and multiply by what? The 8 pounds. I can cancel the pounds, and I have 40 over 12. That's what's left, correct? And that was in dollars. And then, of course, we said, well, gee, I can go ahead and I can reduce that because 4 goes into here 10, 4 goes into there 3, and I get exactly the same answer, which is 3 1/3 dollars. Now, what do we call this process? Dimensional analysis, right? That's where we've been. This was dimensional analysis, the how much unit. Now, what I want you to see is I could have done it as a what? Sliding this over as a proportion. Now, some of you have argued the case that I don't need to do either of those. I can do it in my head. Bless you. And some of you can, and that's called proportional thinking. So if you can do these problems in the following spirit, you go to the market and you find out that it was $5 for 12 pounds and you're going to buy 24 pounds. I hope you know you're going to pay $10 without setting it up with dimensional analysis, without doing a proportion. If it's 5 pounds for $12, 10 pounds, I should say 24 pounds is going to be $10. Twice as many pounds, twice as much money. Proportional thought. Now our problem is if we get weird on this and say I don't want 24 pounds, I only want 8 pounds, then it's not so easy. And that's when we resort to one of two things. Proportions or dimensional analysis. This, under stress, goes. You familiar with Charlie Brown? Comic strip still there. Okay? Schultz was the person who did it, but Charlie Brown. And Linus, when I say Linus, does anything pop into your head in Charlie Brown? The dirty blanket gets drug around, right? He drags it in the ground. It has to be. I mean, it just has to be. You try dragging a blanket around for 20 years and see if it stays clean. Now, my point is, Linus is a caricature of a very young child. Very young children have real trouble with a probability problem. Now, if I put red and white markers in a bag, half and half, young children can get pretty much the idea that it's about the same chance of getting a red as it is a white. But if I now pull all the whites out except one and replace them with reds and ask the child, what's the chance of getting a red marker? Is it more or less? They have no idea in the world. They don't do proportional thinking yet. As an adult, under stress, we become Linus with the blanket in our thinking. Under stress, proportional thought really goes away. And that puts us at a risk. What can you replace it by? Algebraic proportions or dimensional analysis. And that's the argument for it. Because under stress, your ability to do this proportional thought will disappear under enough stress. Proportional thought is what characterizes you from Linus carrying the blanket around. Part of your maturity is to get to the point where you do proportional thinking. And ultimately, that allows you to do fairly abstract thinking and analysis. And of course, the mathematics is trying to give you the symbolism and the structure to do that. So this second section has so much going in it about thought processes, proportions, dimensional analysis, and under stress of an exam, what happens to your head. And where you basically go into a fetal position, grab Linus's blanket, crawl under the table, and quit thinking. Confidence, maturity, and a lot of problems that you practice on are supposed to allow you to sort of leapfrog that moment of panic, crawling under the table, grabbing the blanket, popping the thumb into your mouth, and that's it. That's what we're trying to get away from. Back to the book. Proportions. All in that one little problem. That's what's involved there. And there's a lot of ideas and concepts that I'm sharing there. Just in passing at the top of that page, I can't pass it up. Just a reminder, what do we call this as we show it on the screen? What is the name for that? Complex fraction. In the left side, complex fraction in the right side, correct? But it's a proportion because I have the proportion of two sets of complex fractions. So what do? Make the left side a simple fraction, the right side a simple fraction, and then if you want cross multiply, or, this is a neat idea, just cross multiply with the fractions the way they are. So it's sort of a neat idea that you wouldn't have thought of doing, I think, at this point, if you wanted to go ahead and set up a proportion. And by the way, why in the name of God would we do this? What are you trying to establish up here? Whether these two are equal. They are equal if the cross products are equal. So if you take the cross product and it's not equal, those two fractions are not equal. Michael?
How would you do the cross product of the complex fraction?
Well, the cross product is shown right here, where I have 3/4 times 1/2, and then take 3/10 times 5/12. And that's what's shown here, and you don't get the same answer. 3/8 is not 1/8, so those two are not equal. Now, there's other ways of doing that, but that's the whole idea in that one. Solving a proportion problem. I think this is rather neat because you would translate it in an entirely different way given Math 10. I'm on page 518. Bobby can read 40 pages in 50 minutes. How long will it take him to read 220 pages? What kind of problem is it? Coming off there, dimensional analysis. Or you can do it as a proportion. Well, the dimensional analysis would be your how much problem. But as a proportion, this is where you get a chance to see it in a different way. Just set up the two fractions and solve for the missing part of one of the fractions by cross multiplying. You'll get the same answer. You have to be able to do it both ways. So one of the things I was very excited about with this book and continue to be excited about this book every time, and we're up to 518 pages. This has been a review, if you will, looking back at every step of the way what we did in Math 10 and totally consistent. And I'm constantly in a position where I can say, remember what we did there, here's what we do here. That is the beauty of it. Now, the downside of it is at times, I think it gets a little bit intimidating because the algebra part takes you a next step. My hope is that you get enough of what we're doing in the algebra part, and that's where my focus tends to be in the quizzes, that when you then go into a Math 70, you're going to be prepared. As it has been in the past, I haven't had the feeling that going out of a 20 prepares you for the 70 the way it should. I've got a really good feeling about this book in terms of what it's doing if you hold up your end of the bargain. And that is really putting the effort into it, doing the problems, giving it 200%, then I'm very confident that this is about the best way we can do a Math 20. I am super pleased with what this book is allowing us to do and the things it allows us to see. Now, I'm also very conscious that if any of my colleagues look at the tapes and look at what I'm doing, I think they're going to have the gut-level feeling based on their classes, man, you're going too far. But I have an advantage. Every one of you has been in Math 10. In their classes, hardly anybody's been in Math 10. And there is a huge, huge difference. They end up having to concentrate nothing but the arithmetic. And that's all they get done, and they don't have a chance to cover the content that is really algebraic. I've got the advantage in my mind. Now, whether or not this is scary to me. My advantage, I believe, is you remember what we did in Math 10. That is a really big assumption that you remember, because I know what happens to any of us in 2 weeks after the semester ends. It just disappears in our head. So that brings up the question that I do want to comment on. What should you do having this background in terms of taking an algebra? And I don't necessarily want to suggest that you put yourself in boot camp. Boot camp is called summer session, 5 weeks, 4 hours a day of algebra. I don't care how much you like it. It's dangerous. Now, a lot of students do it, but be aware you're going to eat, breathe, live, and sleep 40 hours a week algebra. If you decide not to do that, then you get study groups, study sessions, and you keep hammering at this all summer long. Because if you come back 15 weeks later, it's not going to be there. That's the dilemma of taking 20 in the spring. Okay, we've talked about how much. Next topic. Geometry, trigonometry. 2 right triangles. Now notice, this is your classic Pythagorean triple, 3, 4, 5. Do I need to say more about the 3, 4, 5? I hope not. Now I made a comment to you. I'm going to have to pull that down just a little bit. There is a very easy version of the 3, 4, 5 that in carpentry works better. Instead of going 3 feet, 4 feet, 5 feet, or 3 inches, 4 inches, 5 inches, double everything. So if that were in feet, you go 6 feet, 8 feet, 10 feet. We say that these 2 triangles are similar. Okay, similar triangles, and notice the triangle is designated by its 3 angles, A, B, C, D, E, F. And notice this goes, and I'm bothered by this. This irritates me. This should be A, B, C with C the right angle. Not enough carefulness here, because C is typically the right angle, the legs are A and B. So this is messed up. But it's alphabetical. And this is D, E, F. Now, this sets up proportions. We say that this AB is to DE as BC is to EF. Proportional parts. So the short leg is to the short leg as the long leg is to the long leg. We set up proportions. And so that is where you find this statement down here. There are a variety of them. But you have 6 is to 3. Okay, so that was the short leg for both. So 6 is to 3 as the diagonals are to each other. Or I can say the short leg to the long leg as the 5 is to 10. I don't see this done quite the way I'd like. I would like to have said 6 is to 3 as 8 is to 4. Proportional parts. So we say that we have proportional parts coming off there of similar triangles. Now, note it's generalized here, not just to triangles, but in the middle of 520, it's called similar figures. So I could have trapezoids that are similar in the same way that I can have not just right triangles, but here are two generic scalene triangles in which they are similar. You understand the zoom part of a lens, the zoom part on your computer? You just increase the size of this one so it's this size, but the angles are the same. The three angles are all the same. It's sort of like shrink me down to the smaller version. Those are similar triangles. The rest is trying it with exercises. Now, I've tried to choose fairly carefully, and I've avoided the similar trapezoids. I have kept it with similar triangles, so everything I've said today should allow you to do what I've talked about, and I did include one problem from the Boy Scout manual, the last problem in the section. So you have 7.1 and 7.2 to finish up this weekend. We'll have our tutorial tomorrow to answer questions. I am out of time. We're going to go back to Joni Mitchell.